Hello, my name is Stefano Pellerano. I'm from Intel Labs at Intel Corporation. In this short talk, I will introduce you to the fundamentals of millimeter wave phased array transceiver design for 5G applications. So the first question to ask is, why do we want to build a transceiver at millimeter wave frequencies? Now, we know that 5G is meant to deliver multi-gigabps data rates to the users, and this means that channel bandwidth in excess of 200 megahertz are very likely to be used. We also see that the spectrum below 6 gigahertz is very crowded, and so it's unlikely that we will be able to allocate new channels in this band. There are also fundamental fractional bandwidth limitations in the design of both the transceiver and the antenna. For example, if we take this simple example of a dipole antenna designed in a constrained volume of a sphere of a radius A, we can see that there is a trade-off between antenna gain or efficiency and the actual bandwidth. And you can see in the equation here on this slide. So as we increase the bandwidth of the antenna, reducing the Q, of course, the gain of the antenna itself will go down. Same or similar can be said for a transceiver design in terms of power consumption. You can see here another very simplified example of a tuned amplifier where we see that if we want to keep the same small signal voltage gain, but we want to increase the fractional bandwidth, we very likely need to increase also the power consumption. So then this drives us to design and use a new frequency band at millimeter wave. First of all, because here we have access to large continuous spectrum, which is available, but also because now we can use with the same fractional bandwidth wider RF channels. So there are several opportunities for 5G in terms of spectrum, and these are basically still in progress and changing almost every day. Interestingly, like almost the entire cellular communication happens in only about 1 gigahertz of compounded bandwidth. Instead, these new opportunities account for almost 30 gigahertz of new bandwidth. So the 28 and the 38 gigahertz license band is already under development by 3GPP and offer about 3 gigahertz of bandwidth overall. We then have the ISM band. There are already products on the market in this band. It's originally from 57 to 64 gigahertz, but also this has been extended up to 71 gigahertz. Then we have two bands at 75 and 85 gigahertz. And these are quite attractive as millimeter wave bands because they offer 5 gigahertz of contiguous license spectrum, and these are currently being proposed for 5G. Now, one question to ask is, how about path loss at millimeter wave? Is it worse than what we see normally at sub 6 gigahertz? Now, if we look at the free space path loss equation for omnidirectional antennas, the answer seems to be yes, because the equation seems to indicate that actually the loss scales with the inverse of the square of the frequency. However, if we rewrite the equation for antenna aperture, what we see is for constant antenna aperture, which is in a sense related to the size of the antenna, the path loss is actually independent of frequency. And this can be intuitively explained looking at the figure here on the right. We can imagine to have a transmitter radiating energy, and this energy is propagating as a sphere. And so the energy is spread across the surface of the sphere. And so at a distance d, if we have an antenna, the power that the receiver antenna will be able to capture will depend from the intensity of this field, which is power spread across the area of the sphere. You can see this explains the dependency from d square, but proportional to the effective area of the antenna, which is the effective aperture. So we need to keep the same antenna aperture, and then the path loss will not increase. And antenna arrays are a perfect way of scaling up the frequency of the carrier by keeping the same antenna aperture. However, once we introduce an antenna array, we also introduce antenna directionality. And so in order to have omnidirectional communication, we need to introduce a way of doing beam steering. Now let's look at principal operation of phased array. So this plot shows an idealized electromagnetic field radiated by one isotropic radiator placed here. And this plot has units that are normalized by the wavelength lambda. So now if we add a second radiator placed at half wavelength here in phase with the first radiator, you can see that now we don't have an isotropic radiation anymore, but the beam, we can see the shape of a beam. And the beam width, as we increase the radiators to 3, to 4, and 5, we can see that we are creating a narrower beam. So we are able actually, by using a phased array, to create antenna gain and create a beam. But now that we have a beam, how do we actually steer this electronically? For this, let's consider a simple example where we have two elements spaced by half wavelength. Let's assume that we have continuous wave signals. And so in order to steer the beam towards the elevation theta, what we need to do is that we need to make sure that we have constructive interference along that angle. And to do this, we simply have to introduce a phase shift phi here to compensate for the phase shift accrued due to this path difference delta L. And this can be easily calculated with simple geometry and is indicated here in the slide. So now we can go back to the previous plot where we had all the radiators in phase. And say, for example, we want to steer the beam by 20 degrees. We can actually use the equation in the previous slides, calculate what the phase shift is, and apply this phase shift to each element. And you can see now the beam is not pointing towards the horizon, but is actually steered by 20 degrees. So what we said holds, of course, for continuous wave signals. But in reality, theoretically, what we would need is not really phase shift to compensate for this delay, but actually, as I said, delay, we need a tau delay equal to the ratio between this difference in path, delta L over c, where c is the speed of light. For a CW signal, a time delay is effectively equal to a phase shift at a specific frequency f naught, as you can see in this plot of phase versus frequency. And this phase is effectively equal to 2 pi f naught times the delay tau. But the moment we use wideband signals, or we start deviating from the frequency at which this phase shift has been calculated, as you can see in this blue line, the error in the phase shift effectively increases with the frequency deviation delta f and the delay tau. So this problem manifests in the effect known as beam squinting. So beam squinting is the change in beam direction as a function of frequency and orientation that happens when we have a broadband signal and we're using phase shifting for the phased array. So the beam steering error can be estimated and is shown in this equation as a function of course, the center frequency at which the phase shifting has been calculated and the frequency deviation delta f and the steering angle. Now, in order to not impact our array gain, what we have to do is we have to make sure that this beam steering angle is much less than the actual beam width. And this, interestingly, imposes a limitation again on the fractional bandwidth, which has to be much less than this ratio, where n is the number of elements, considering a linear arrays of elements all spaced by half a wavelength. So looking at this equation, it is clear that if we start building a very large array with a very wideband modulation, we probably need to have true time delays instead of phase shift. But these, of course, are quite difficult and challenging to implement in IC technologies. Now I want to do some consideration on phased array link budget. So let's start from the receiver SNR. So we have several elements, and so if we assume that the noise coming from each element is uncorrelated, we can see that the signal will add coherently. And so overall, we have a 10 log n array gain for the receiver for the SNR. For the transmitter, we have two combined effects. The first one is just the fact that we have several power amplifiers that combine all their power. And the second effect is the actual antenna gain. So overall, for the PRP of the array versus single element, we have a 20 log n gain. So now let's do this thought experiment where we try to compare a single element implementation versus a phased array implementation for equal DC power. So for the receiver, we can take the many element. We can scale each element by 1 over n in terms of current. So overall, when we take the array gain into account, we will have the same power consumption, but also the same noise figure. So we don't have any gain or loss compared to the single element implementation in the receiver. Now we're looking at the transmitter. Assuming the same number of elements of the receiver, we can again scale the power of each element by 1 over n, the power consumption. But still, we'll get overall a 10 log n gain in the PRP. So by looking at things together, we can see that compared to the single element implementation for same DC power and antenna aperture, we have an overall link budget gain of 10 log n. Of course, this is a simplified analysis. It assumes that we are in a noise-limited situation for the receiver, and also does not take into account the potential power consumption overhead introduced by the phase shifter. Okay, I will now go through few potential architecture for transmitters to implement beamforming. We will focus on receivers, but same consideration can be also used for transmitters. The most common beamforming architecture is called RF beamforming. So we placed the phase shifters at RF, and we typically place this after the low noise amplifier to mitigate the impact on the overall system noise figure, since this phase shifter can be quite lossy. In terms of advantages, we can see that this architecture is fairly efficient in terms of power consumption and area. We have a spatial filtering done right at RF, where we combine the signals, and so this relaxes the linearity of the mixer and all the successive blocks in the receiver. And also we can easily add a beamformer front end to an existing transceiver design. The disadvantages are that these phase shifters have to be implemented at RF, so can be quite lossy. They are on the signal path, so they need to satisfy the bandwidth and the linearity, and this architecture in general can only receive a beam from one direction. Another very similar architecture is the LO phase shifting, and this is kind of equivalent to RF phase shifting. And now here the phase shifters are actually inserted on the low path before each mixer. This is actually can relax the phase shifter linearity and bandwidth, because now the phase shifters they are actually on the low signal, so they can be implemented almost like digital delays. And if we have one synthesizer per element, we can actually embed the phase shifting function into the synthesizer. Some disadvantages are, of course, a potential increase in the low power due to mixer load and also like longer and low distribution. Mixer linearity is more demanding here because we don't have a spatial filtering before the mixers. And again, this architecture can only receive one beam. Yet another one is analog baseband beamforming. Here we move the phase shifters after the down conversion stage. And this can be implemented, for example, by just mixing IQ and implementing a phase rotation. In this case, the advantages are that we have potential minimal phase shifter loss because the phase shifters are implemented at low frequency. And so it's kind of easier to implement higher resolution phase shifters. Disadvantages are that, again, we have a potential penalty for power and area overhead, and also receiver linearity, because now also the phase shifters needs to be linear. And they're also on the signal path again, so we need to meet the bandwidth requirement for the signal. And this architecture, again, can only receive one beam. And finally, another architecture to mention is the digital beamforming. Here, we basically have an entire receiver for each antenna element. And after the conversion to the digital, we do the phase shifting in the digital domain. So the phase shifters are effectively complex multipliers. This is a very flexible and reconfigurable architecture. Can receive multiple beams from multiple users, can actually implement full MIMO, and the phase shifters are lossless, and the resolution of our phase shifting is limited just by the digital precision. This architecture is very useful when we need a fast beam or acquisition, because this system effectively can look in different directions at the same time, and so can quickly understand which is the direction of arrival. Some drawbacks is that there could be a potential increase in power and area, because now we have a complete chain of receiver replicated per element, and we don't have any spatial filtering for the entire receiver. So again, linearity requirements, and in particular for the ADC dynamic range, especially in case we have interference. Okay, now in conclusion, we've seen that millimeter wave carrier frequency can enable wideband modulations, and several millimeter wave bands are already being considered for 5G. And the free space path loss of millimeter wave is not worse than sub 6 gigahertz if we keep the same antenna aperture. And this can be done efficiently by using arrays of antenna. But of course, once we have arrays of antenna, we introduce also directionality, and so we need to have a way of doing beam steering to maintain spatial coverage. We also see how phase array can improve link budget compared with single element implementation for the same power antenna aperture. And that there are several architectures that can be used for beamforming depending on the application. So this concludes this very short introduction. Thank you for watching, and you have my contact information on the first slide, so feel free to contact me if you have additional questions. Thank you.